Welcome to the It's Language Technology webinar series. I think you can see the outstanding list of speakers that we had this year, well, this course, starting from last summer, and it's an honor for us to have Mirella as the last, but also one of the most interesting speaker in the lineup. So Mirella is very well known, but just in case, I'll give some notes that you can read here. She's a professor in the School of Informatics at the University of Edinburgh, a great place to do research, I can assure you. I was visiting there after last summer and last autumn. She had several prizes and especially Best Paper Awards. And also she had responsibilities, editorial boards of relevant journals, president of SIGDAT, which is the one organization which organizes EMNLP, one of our prime conferences. And she's enjoying an ERC consolidated grant, which is one of the few that we have in Europe in NLP. And she always has exciting things to say. So today we'll talk about well, you'll say this, I'll stop.
Thank you for a lovely introduction. Okay, yes, please visit us in Edinburgh. It's a lovely place. Okay, so the title is Prompting is Not All You Need, or Why Multi-LLM Collaboration Matters. And it's really the latter point. So I'll show you throughout the talk examples of how these language models collaborate together. And I hope I'll motivate why this is a good idea. And the talk is not, I'll try, like, I want to have discussion, so I will not plan to fill the entire hour. Okay, so let's start. So I want you to look at this.
Sorry, Mirella, yeah? We are not seeing the slides, but that's because I share mine. So can you reshare again?
Yeah, of course. Okay.
I think
I'll share. Yeah.
Yeah, you started to share, but then I shared mine, so I interrupted you.
No problem. Let's see.
Very good.
Okay. Okay, there we are.
Great.
Okay, right. Let me remove this here. Okay, you can see?
Yeah.
Okay, right. Okay, so let's look at this graph. This graph was created by this company called Life Architect, and you can find it on the internet. And what they're trying to do, if I had to describe them in one word, is they are an aggregator of all the things that happen in our community with regards to language models. And they create these cute graphs. So this graph here, if you look at the bar chart, the blue, tracks the number of language models that were released throughout 2024. And you can see, for example, that February and April were good months. 28 models were released in February and 26 in April. The red plot, it's one of these like psychedelic bar charts where there's two graphs in one. So the red line here, you have to look at this axis here. The red axis is the number of LLMs released per hour. So here, low numbers mean a lot of LLMs get released every hour. High numbers mean that, you don't have so many LLMs being released. So you see here 62. October is a month where we didn't have that many language models. Why am I going on about this? I'm going to show you this graph in two different ways. So to understand how many of these models get released throughout the year. So the blue bar chart is the new derivative language models released per month on Hugging Face. And by derivative, we mean some company or some institution will release a language model, and then you take this language model, you change something, and you release the checkpoints on Hugging Face. And we see here that they're in the tens of thousands. These are derivative language models that you can just go and download. And the red bar chart shows again, the hourly rate upon which these models get released. And lower means more frequently. As you see here, February, for example, was good. Many models were released. So we're talking about thousands of models out there that people release. I don't know who's using them, but there's lots of them. Okay, so And if you see the trend, so this is another company that creates these graphs, Epoch AI. And if you see the trend, and this is not surprising, as to how the training compute changes, or the needs for training compute change over the years, we'll see that within 14 years, from 2010 to 2024, compute has changed. I mean, the demands is 4 times every year. So we need 4 times more compute for every year. And you see, it's almost like it grows linearly. So we have a lot of language models, and they all need a lot of compute. So the next question that you may want to ask is, how good are these language models? Again, there is this Life Architect company that has taken and tested all these language models, and these are mostly proprietary ones, and except for Mistral, I guess, and they give them a quality index. So now this is not a metric that we in academia would actually care about that much, but it is a composite metric of how well these models do on these different leaderboards. They have like all these leaderboards that they have to do well on. And what you see from this graph, so this is the quality index, and higher is better. You see like here, 03 mini is like maybe the best, but there is a slow degradation in quality, but there is no language model that performs best. In fact, we see like there is the majority are on the same sort of level, middling some way, with scores between 49 to 40. So nothing jumps out. Like the quest for the best language model continues. And there is a school of thought that seems to think that we can find one language model that can do everything. And my hypothesis here, or what I'm trying to convince you, is that probably there is not a single language model that we can develop that will do best at everything. So, and there is 3 important reasons for this. So the first reason is that these language models are trained on these static snapshots of the data that is available out there in the web. And so there's always elements of real language distributions that will be missing. So there's always going to be case, maybe this is not the majority, where these models will be asked to perform tasks that are out of distribution. And until we actually change our architecture so that they can generalize, out of distribution presents a problem for these language models. And out of distribution could be different languages, could be different domains, different styles. So first of all, they don't do well out of domain. Secondly, it is quite expensive, or maybe one might argue impossible, to have one model that can do everything, that can outperform all other models on all skills. So I would argue that there is no single LLM that is Pareto optimal. You will have some skills that it does well on, and some other skills it doesn't do well on. And these skills may be reasoning skills, or communication, or creative, if you care about creative tasks, or even technical. And we see that people start to realize this, because we have these LLMs nowadays that are like specialized for code, or for video generation, or for specific tasks. And this is a realization that, in order to do well at the task, you have to have like these specific capabilities. Now, the third argument as to why there won't be one language model that will rule them all has to do with alignment. So ultimately, we put these language models out there to be used by people, and people have different needs, have different values, and different backgrounds. So the users are not like whatever companies or outfits think they are. So if you, again, put these models out there, the alignment, you will probably have aligned the model you see here for one user, but there is a distribution of users that have different opinions, values, and cultural norms that we will not be able to represent. So if that wasn't enough to say that, one language model is probably not the solution to our problems, There is another real life argument, which is how people function in the real world. So this is kind of a busy picture, but this is what happens when you are in an operating theater having open heart surgery. And this, I actually took this picture from an actual journal where they were talking about a new method that they invented to perform heart surgery. The point here is that if you're in this operating theater, there is many individuals that have specialized roles, and nobody assumes that there will be one person, one heart surgeon, and she will actually do everything. She will do the monitoring, the operation, take care of the patient. So here, in the real life example, we have expert operators, we have assistants, we have an anesthetist. So everybody is specialized, and of course they interact together and they communicate. Okay, so you know what's coming now. There's some good arguments as to why we shouldn't be doing everything with one model. And then the question is actually, how are you going to be solving tasks if you involve multiple models? And this brings us to the distinction of single versus multi-agent systems. And this is an ancient picture. I actually went and took it from an AI book from 2000 something. It's a really cool book, but it gave me the visuals actually explain what the main difference is between single agent systems and multi-agent systems. And there is a lot of confusion in the literature. If you have like a model that calls tools, people call it agentic, but it's not a multi-agent system. It's a single agent that can call tools. So if you look at these ugly pictures, but actually the abstraction is fine. To have an agentic system, you have to have an agent, obviously, and the agent you define will have goals, actions, will have some knowledge, but there will be an environment, and the agent goes and does some actions in this environment, and there's consequences. So there is a cause and effect. And this you can see here as I'm looking at it on the left-hand side, this is a single agent. Now, the interesting thing about a multi-agent system is that aside from having the agents that do the same, they have goals, they have actions, they have knowledge, and these are different. And the fonts here indicate that they can have like a different set of actions and a different bits of domain knowledge. They also have an environment and they act on their environment, but the important point is that they communicate. And this is a very important thing that differentiates multi-agent systems from single-agent systems. They have what is called a shared persistent state. So this is a mechanism for passing context from one agent to another so as to enable the collaboration. So the agents actually have access to the actions and the effects of the actions in the environment. And this is like the most important thing is, so how you make this persistent state, it's a designer's choice. And I'll show you one way of doing this, but it's important to have it. Okay, so let's contrast the two types of systems more directly. So if you have a single agent system, the agent is independent, it operates autonomously, and it doesn't rely on other agents, goes and does the task. Whereas if you have a multi-agent system, you expect the agents to interact and collaborate to complete these tasks. And usually we give them more complex tasks. And of course, there is this interaction element. So it's a bit more complicated because you have to manage the interaction. Now, a single agent system has less components, there is less integration, and you can, it's from conception to actually realization of the single agent system. It is easy. However, you cannot assume that it can deal with new tasks, new skills, new environments, new users on the fly. You will probably have to do something about that. The multi-agent system, the theory goes, can handle diverse and challenging environment. I'm not going to show you examples of different environments, but the theory is, if you have agents, they don't have to do things together simultaneously. They can run processes in parallel, and that makes them more fault tolerant because, if one agent is off, the other agent can pick up the tasks. And usually they are distributed in the real world if you had like an engineering system. Now, the way we do the single agents, we learn from some external feedback. So you have your pre-training, and then you have the instruction tuning, and then you have the reinforcement learning, and you do this once. And then that's your model. And you assume that it can do multiple tasks. Whereas if you have a multi-agent system, you have richer data, you have interactions, you have shared experience, and learning can happen multiple times depending on the tasks. So, you know, I'm thinking of, you have like 5 agents that have specialized properties or specialized actions, and then depending on the task, you could potentially learn different ways of orchestrating these agents, and we'll see an example later on. So this is a bit more flexible. Okay, so now, if you want to play this multi-agent game, then there is many decisions. This is the problem, right? You know, a single agent, you have to make some design choices, and then that's it, you're done. Here, you have to decide what you want to do. And there is different flavors of how you engineer a multi-agent system. You can assume that the agents are cooperative. And I'm only going to show you examples of this category, like they collaborate. So they all collaborate towards a common goal. They could be competitive, so like they debate and, you know, they decide who's right or wrong, and then you achieve your goal. You can have a mixed variant where some agents collaborate and then they play against another agent. You can have hierarchical, where the top agent is the boss and decides who are the agents below him or her. And then you can have orchestration, where you have your agents and the agents operate in their environment and their shared environment, but there is an agent who is the orchestrator that decides which agent to call for a specific task. And this is, if you like, the most flexible architecture, because it's not hard engineered. Here in hierarchical, we have done the hierarchy, we cannot undo it. Whereas with orchestration, you create this controller, and the controller can choose which agent to call and in what order. It is a bit more flexible. Okay, so let me, there's 4 questions we want to answer in this talk. So first of all, which tasks are suited to multi-agent architectures? So if you have a task, should you do a multi-agent architecture or not? I'm not going to answer this question directly. I'm going to show you some tasks for which multi-agent architectures are good for. Then the second question is, once you want to build this system, how do you specialize the agents? What do they do? How are they different? How do they communicate? What is this shared persistent state? Again, I will show you one flavor. And then the other question is, if you go through all this trouble of actually putting the agents together, what do you gain? Maybe you gain performance, but I would argue you probably gain more explainability. And again, you can see if you have a multi-agent system, how the different components contribute to your task. And so you actually understand what you're modeling. Okay, so for the remainder of this talk, we will use these collaborative agents to perform writing tasks. And by writing tasks, I really mean creative tasks like story generation that are insanely difficult. I mean, the task is difficult. Not how we do it is difficult, but if you want to generate a story, you'll see it's like, yeah, difficult. Right, okay, so let me show you the task. The task is like standard in the literature. So you have a language model or many language models, and the task is I have a prompt, and then I want the model to actually write a story based on this prompt. And this prompt here has been taken from the New Yorker, and I'll read this out to you because it gives you a flavor of what we give to the system. So obviously this is a joke, but it says, please tell me a story about a puppy who goes to Jupiter on her birthday to solve a mystery and is a mermaid. So the puppy is a mermaid, goes to Jupiter, using an engaging and humorous tone in approximately 1,000 words in the style of Ernest Hemingway. Now, this is an insane prompt, but we will give prompts like that are a bit detailed and say things like, I want you to write a story about subjects X, Y, Z, and I want you to keep it light with comedic style and whatnot. I'll show you an actual prompt. So once we give that prompt, we want to actually generate a story that is faithful to what we've instructed the system to do. Okay, so obviously, given what I've said so far, we're going to have these agents. So the question is, what will the agents do, and how will you have different agents represent different bits of the story writing task? So before I present the actual agents, let me tell you a little bit about what is the theory of writing. So basically, there's two things that people do, both of them together when they write a story or a book. The first one is everybody agrees that there are some elements of narrative technique. So when you're about to write a story or a book, you have to decide who are your characters. So for Harry Potter, for example, we'd have to decide that, you know, Harry Potter is a young wizard and this is our main character. Then there has to be a theme, good versus evil. There has to be a plot, like what happens, young wizard goes and kills bad wizard who has become like really dark. This would be in Harry Potter. Then we have a setting. So the setting in the Harry Potter case is like the school, the Hogwarts School of Wizardry. Then there has to be a conflict, like good versus bad, good versus evil, and a point of view. So in J.K. Rowling's novels, she is actually the narrator that knows everything, the omniscient narrator, and she tells the story. This is the point of view of this book. So these are core story elements that the person who writes the story, not the machine, has to decide, the theory goes, before actually going and writing the task. So you kind of plan what your story will have, what are the elements. And it's no surprise that some of our agents will be based on this. So we'll have an agent for character, another agent for plot, another agent for the setting, and so on. So this is the first bit, which is, you know, you decide what's in your story, and then it's how you write your story. And this dates back to Gustav Freytag, who was a playwright in the 1800s, and he is credited with the Freytag pyramid. And you see it here. Well, it's more like a triangle, but it's really a pyramid. And so what Freytag says is, you know, when you're actually writing the story after you've decided what should be in it, you need to have like some pacing. And so you start with the exposition, you frame the story. Once upon a time, you know, there was a baby found next to a house, and this is like young Harry Potter. So there has to be an exposition, then there has to be an inciting incident. So then we start building the narrative, the action rises, then we climax, there is a key point of the narrative, and then further, then there is like, the action falls, and finally there is a resolution. So basically a story, if you like, there's 4 parts or 3. You frame the story, this is the beginning, you build the narrative, and there is a call to action. And there is a school of thought that thinks like all stories have to be like that. And if you look at Hollywood and the movies that Hollywood makes, a lot of them, a lot of the screenplays to this day follow Freytag's pyramid. So we're going to have 2 kinds of agents: the planning agents that tell us what's in the story, and the writing agents that will actually write the story. And try to be faithful to Freytag's pyramid. Okay, so how do we build this multi-agent system? So we're going to have an orchestrator, and the orchestrator will pick in between planning and writing agents. Okay, and the input to this orchestrator will be the prompt, a prompt like the one that I showed to you, with a dog, with a puppy that goes to Jupiter, and is a mermaid, and blah, blah, blah. So we'll have a prompt here. And depending on this prompt, the orchestrator will first go into the planning agents. So the planning agents are based on the elements of narrative theory and will write the conflict. The conflict agent will write stuff about the conflicts, the plot agent will write the plot, the character agent will write things about the character, and the setting agent will write things about the setting. What I'm showing you here, these bits here, is the scratchpad. So remember, we have to have a shared persistent state, and every agent needs to have access to what the agents before them has produced. And so conflict we write to the scratchpad, the conflict of the story. Then the scratchpad will serve as input to the next agent. So the plot agent sees what the conflict agent has written. The character agent sees everything so far, and so on and so forth. And so we're building this scratchpad, we're not deleting anything from it, and the scratchpad serves as input to select the next agent. Once we finish with the planning agents, we'll move on to the writing agents, where again, similarly, the orchestrator will pick the exposition agent, the rising action agent, the falling action agent, the climax, and the resolution. And this follows Freytag's pyramid. An important point is that the planning agents write to the scratchpad, but not to the output. The writing agents read the scratchpad, write to the scratchpad, and also to the output. So once we've created all of that, then in the end, we'll have our story. I have an algorithm to a bit more formally explain how it works. So we start by initializing the scratchpad. And again, scratchpad, you can think of it as a memory or this shared persistent state. And in the beginning, it will be empty. So then the orchestrator is tasked with deciding which agent will go first. So the orchestrator assigns the next agent, and it does this by selecting the agent given the scratchpad. So we read the scratchpad, we see what we've produced so far, we select the next agent then does its bit, generates some information, we obtain this output, we update the scratchpad with the agent's output, and we keep doing that till the end. Now, importantly, if the agent is a writing agent, we also write to the scratchpad and the final output. And we iteratively go through all our agents, and then we produce the story. The one other important point, and this is a technicality, we have to label the agents with this L sub T to know, this is important part of the learning, to know which exactly agent you are writing to the scratchpad, so as not to confuse them and have like everything like a salad. Now, another important point here is that the way I've decided, I've sketched this, I have an orchestrator. The orchestrator picks the agents, but the order upon which the agents are picked is decided by us, the developers. There is no learning, so to speak, to decide, for example, for this prompt, I don't need to have like so many planning agents. Deterministically, we follow this order of picking the planning agents first and then the writing agents. And I'll show experiments I have experiments later on to show, is this a good thing? Is it a bad thing? What is it? Okay, so let's see what we've done so far. So we have this multi-agent framework for this complex writing task, and we decompose the writing problem into subtasks, and each subtask is performed by a specialized agent. And by agent, and I did not make this clear, assume an LLM here. That is specialized differently. So they communicate collaboratively, they can plan and write, and they are a language model, and you can have two variants. You can have zero shot where you do nothing, or you can have a fine-tuned agent for the task. Now, for the remainder of this talk, I will show you results only with a fine-tuned agent. So we create an agent that is fine-tuned for writing the theme, is fine-tuned for writing the character, is fine-tuned for the plot. And you can ask me how we did this. You can imagine it's not that important to the talk. All I'm going to say is that the results are with the fine-tuned agents, and these are specialized. The scratchpad is the shared persistent state, and the orchestrator is deterministic. Now, the experiments were run on this data set called Tell Me a Story. And this data set is interesting because it was elicited from professional writers who actually know how to write. They all have degrees in writing, or they write for companies. The way that the stories were elicited was quite interesting. The writers sat in a room and they gave feedback on each other's story. So I think confidently I can say that these stories are high quality. They came also up with the prompts, what kinds of prompts would be interesting for stories. And so aside from the fact that they're not like synthetic, they're actual stories, they're also very long. They're up to 1.5 tokens long. So this is a good story. So you can have like beginning, middle, and end. It's not like 5 sentences. And all the experiments I'm going to show are based on Gemini models. And I can answer questions as to, how smaller scale models do and whatnot. Okay, so what we're going to have here, we're going to have planning agents and writing agents, and the orchestrator picks which ones to write on the scratchpad. 2 important points. The planning agents just write to the scratchpad. The writing agents write to the scratchpad and the output because they generate the story. Now, for the experiments, we're going to compare basically 4 things. And again, there is more comparisons in the paper, but I'm happy to answer questions if there are any. But to get the gist of why this is working, there is these 4 experiments that are essential. So the first of all is to create an end-to-end baseline. And by end-to-end, since we have these data sets, of stories and prompts, we can basically fine-tune a system to learn to generate the story end-to-end. So no multi-agent system, nothing. We just inject some story writing capability. So this is our first baseline. Then we can just have planning agents. So we just plan the story, give this plan to the model, and then write to the output. That is a baseline. Do you need all these agents? Then we have the writing agents only. So we plan nothing. We just go and write the story. And then finally, it's the combination of the planning and the writing agents. Okay. Before I show you results, I want to show you an example of what the multi-agent system does. And by multi-agent, I mean the last one, that it does both planning and writing, and why this is maybe a better way of writing these stories. So this is an actual now writing prompt from the data set. And the prompt goes as follows. Write a short story about a myth or legend being fulfilled in an unusual or unexpected way, or even cleverly bypassed. There's more stuff. And then it says it should take place during the COVID-19 pandemic in Europe. The narrative should involve vampires. The genre should be comedic horror. So now, because we have these agents and they write in the scratchpad, we can actually go and see what they write. So the conflict agent said that, we can surmise that the legend here or the myth is Dracula. And Dracula comes up with this solution to cleverly disguise themselves as a delivery person for Vlad's kebab house. Remember, it's COVID. And Dracula needs to eat. So how is he going to eat? He is this pizza delivery person. And this allows him to move around undetected and deliver blood-sucking pizzas to unsuspecting customers. However, his plan goes awry. So this is, again, the conflict when he encounters a delivery driver from Pizza Hut who challenges his territory and exposes his true nature. So this is very funny. And of course, the genre is comedic horror. And then when the writing agent generates a story, this is an excerpt. It says, "It's the perfect plan," Dracula said, sinister smile spreading across his face. "The people will be so eager to receive their food that they will not suspect a thing." This is part like of Dracula speaking to himself. Now, aside from the fact that this is a good example where, the prompt is followed and the agents do what they're supposed to do, another important point is that because we are actually dividing the task into subtasks and we are writing out things in the scratchpad, if things are not good, a human can go and intervene. So if you didn't like your conflict agent, you could edit your conflict agent. And because the scratchpad is the shared persistent state, the human now is yet another agent that edits its state, and then it gets passed on to the other stages. So this is nice, and also you can see like the different steps of the decomposition. Okay, let me show you some results because there's also a second part in the talk. Okay, so as part of this work, in order to evaluate this system, of course, we had to develop a lot of automatic metrics. However, as we found out, if you are playing the game of I will write a story, there are no good metrics, automatic metrics to assess how well your model is doing, first of all. So, and even if you think you are developing an automatic metric, it is not so easy to show that it correlates with human judgments, because assessing creative writing is a highly subjective task. And experts disagree, and you cannot have like a 0.1 correlation of your metric with the whatever the human judgments you obtain are. So I'm happy to answer questions about metrics for automatic metrics for story evaluation, but I'm going to show you here human judgments. So the system output is given to humans. Humans rate the output along these dimensions you see on the y-axis, the x-axis. So the dimensions are plot. Is the plot any good? Is the story creative, or is it like, regurgitating things that the LLM has seen in its training? Is there a development? Is there a beginning, middle, and end? Do things happen? How is the language use? Is there something like innovative in that? And then overall. And these dimensions were taken from, these are more or less, people tend to agree that these are good dimensions to use when you want to assess creative writing. And then we did pairwise assessments, and then you can think of the expert ratings, some ELO score where we ranked the systems along these dimensions. So blue here is the human stories. It's because we had these human stories. This is the upper bound. This is what we are aspiring. And you won't be surprised to see that blue is better overall, everywhere. On all dimensions, the human stories win. Okay, we're not surprised about this. Let's look at the plot. Again, humans are better, and then the end-to-end system is the red. The green is only planning. The purple is only writing, and the gray is both planning and writing. And we see that if you actually use both types of agents, your plot generally improves. Then if we look at creativity, the same story. You write more creative stories if you use both planning and writing agents. For development, it's not the case. For development, it's better to just plan the story without actually having any writing agents. We think it's too much information and it gets confused. Should it follow the plot or should it follow the writing agents? For language use, again, we see that using both planning and writing agents works best. And if you look at overall, there is a slight, oh God, where is it now? There is a slight, the scale is such, there is a slight win to combine both agents or versus just using writing agents. And just planning is not great. So you need to really involve the writing agents in the process. Okay. So I have some interim conclusions. So first of all, long form writing is hard. At no point did we think we did better than the humans. Synthesizing thousands of tokens in coherent narratives is somewhat feasible, even though the stories are not like amazing. The LLMs on their own and in combination always struggle with pacing, with story development. They're not very original. The stories feel somewhat regurgitated, and there is no character development, even if you do all the things that I mentioned. The agents nicely collaborate through the scratchpad, but there is no reasoning involved. There is no learning. There is no okay, what do we do with this information? Basically, we put all this information in the scratchpad, and there is no way of saying, I like this bit, I don't like this bit, I'm going to synthesize it and generate a different story. And that's what we want to address in the second part of the talk, which is a bit shorter than the first one, actually a lot shorter, which is, can we do some learning? This is an interesting framework, but we want to actually be deciding which bits of this planning and writing to pick to generate the story. Okay, so for the second part now, where we actually do some learning, I'm going to slightly simplify the task. And maybe the task seems harder, but I'm going to simplify it in a way that it is a bit more manageable. So what we're going to do is, again, we're going to generate a story, or we're going to generate some creative output. And this time we will go to the domain of books. So we're assuming we have a book and we want to generate the next chapter. Okay, so assume you are J.K. Rowling or your favorite author, and you've written the first chapter of the Harry Potter book. And now, as an author, as a writer, you are preparing to write the second chapter. And this is the task we're going to give to the model. The model will see the book up to a point, and then we will ask it to generate the next chapter. Okay, so here's a sort of bird's eye view of the task. We have the book, we have, and up to time t, we have actually some information in our hand. And this is what a different version of these planning agents that I mentioned in the first part of the talk. So first of all, as an author, we know we have a global sketch of the story. We know what the book is going to be about. We know what happens at different points in time. And this is a school of thought that assumes that the writers plan their books. There is another school of thought that assumes that, they sit there and the inspiration comes and they take where the writing takes them. We're not following that. We're assuming a very sort of anal writer who sits there and plans everything about their story. And this exists. Okay, so we're not like inventing this. So we have a global story sketch. We have previous, we have summaries about the previous chapters. We have characters. The writers call these character sheets. We know what are the attributes of the characters in the book, and we have the previous chapter. And we also have some information about what we want to be, what we want it to be, what our chapter is going to be like. So we have all this information, and this is provided. These are the planning agents. And then we're going to generate the story. Okay. So for this bit, it's again the same structure. We have an input, and the input here is the previous chapter and the information that I mentioned, the story sketch, the summary so far, the characters, the synopsis, and these are like these are produced in the Scratchpad. And then the important bit is that we actually want to, given this information, we want to learn how to generate the next chapter. And by learn, we want to reason over this information here. Up to this point, we want to reason about what is in our Scratchpad, and then create a reasoning trace and then a detailed plan. And the plan then will be given to the generator to generate the next chapter. And the rest of this talk will concentrate as to how you learn this reasoning trace and this detailed plan, because we don't have it. We are not actually in the brain of J.K. Rowling. We don't know how she decides what to do next. Okay, so again, we have this generation task. The task is collaborative and the collaboration is linguistic. They speak and generate text, basically. There is these three types of agents, the ones that do the planning, the reasoning, and then, the writing, where you write the chapter. We have this Scratchpad again, and we are learning now to actually abstract information from it to generate the next chapter. Again, we don't have these reasoning traces. We need to learn them somehow, and that's the challenge. All the experiments were done on 30 fiction books, and these we made sure were not seen by LLMs. We had to buy them. They were published either during 2024 or after 2024, and all the experiments here are with Qwen 7B models. The average length of the next chapter is approximately 2.5K tokens. So in the previous task, we had 1.5K stories. In this task, we have 2.5K chapters, so the chapters are longer. However, here we have some more information because we have the previous chapter and all this stuff about, what should be in the book. Okay, so how do we train this reasoning agent? So if you've been paying attention, there is like tons of papers that talk about how we do RL if we have preference data. So you have to have some high quality reward where you know which one is the better of two outputs. In our case, this is highly problematic because, like I said, there is no good way of evaluating creative output. So even if I have an automatic score, this score is going to be not that great. And maybe somebody could say you could get humans. Where will the humans come from? They have to read multiple continuations of a book. I mean, the task is impossible. So I say here the datasets are expensive to collect, subjective and heavily story generator dependent, because if you change the generator, all your judgments go away. The reward models need training data, and they are not so great with these long context tasks where the input is an entire book chapter and whatnot. However, there are some reward paradigms if you want to train this reasoning agent with reinforcement learning that do not train a reward model. And these have basically been adopted when people do mathematical reasoning. So this paradigm is called reinforcement learning from verifiable rewards, where we have as input the training data, and then we'll learn a policy, and the policy is trained based on these rewards that are verifiable. And in the case of maths problems, of course, it is easy to do because we either get the right answer or we don't. And so we get some reward if our answer is correct and zero otherwise. So this is what people do when they have to learn mathematical reasoning. And then you train this reinforcement learning algorithm, either you train with a reinforcement learning algorithm such as PPO or GRPO. It doesn't matter, whatever it takes your fancy. Now, why am I talking about this? How can we port this in our task, which is not a mathematical task, and we don't have a verifiable reward? We may be able to do something. So we came up with this idea of verifiable rewards via completion likelihood improvement. And this is a mouthful, and I'll explain. And I'll basically say what the key assumption is first. So we need to have some, at least to begin with, some high quality data set where we have an input X and an output Y, and the output Y in our case, we call it completion. It's basically the next chapter. And that we can take from this data set that we created here, these experiments on 30 fiction books. So we can create data where we have input and completions. And we also need something that will generate the output given some input. Now, the key assumption that we're going to make all of this work is that improving the generator's likelihood of producing the data set, the next chapter, will improve the quality of its generations. So basically, we want the generator to give higher likelihood to, we want the generator to improve its likelihood through these reasoning traces. And we're making this assumption that if the likelihood improves, the reasoning trace is better. So if you see here in this graph, which we try to model it based on this one, where you have training data, you have a policy, you have a verifiable reward, but because the task is more complicated, it didn't work like that. So we have the data set, we're training a policy on this data set. And the data set is input, book, completion, which is the chapter. And then the policy learns to output a reasoning trace and the answer, which will be the plan for the next chapter. We give this to the generator. And the point is, the better the trace, the higher the likelihood. And the way we are measuring this is through this improvement. This I stands for improvement, the improvement of the output given the input and the reasoning trace. And if you have this concept of improvement, then you can define a reward that is based on this improvement. So how do we measure improvement? And given what I've been saying, it will come as no surprise that improvement measures how much an answer, i.e. a plan, improves the likelihood of the story. And there is an intuitive way of measuring this via perplexity. And here you see it's 1 minus the ratio of the perplexity of the model that takes the reasoning traces as input versus a model that doesn't. And then you multiply it by 100. And then once you have this improvement of the output, of the likelihood, then you can define a reward, some simple formulation based on this improvement. And you can have thresholds, if it is below a certain threshold or above a certain threshold, or it could be binary, yes or no. Okay, let me show you what the reasoning traces look like. They are ginormous, and basically it gives you a plan for the next chapter, broken down into 3 steps, based on this book. So Fern's development, the girl's experimentation, the spell, and then in summary, in the next chapter, this is what's going to happen. So the blue is the trace, the red is the plan, and that's what we give to our Scratchpad then here to generate the next chapter. Okay, almost last slide, 2 more slides to go. So this is again same scenario, same dimensions of judging the quality, except that here I'm not including the gold chapters. We did not include them in the human evaluation because in all the tests that we did, overwhelmingly humans preferred the gold standard completions, the gold standard chapters. So believe me, the human chapters are so much better, but that's not the point. The point is whether the reasoning traces improves versus other modeling approaches. So blue is just planning. Red is planning and reasoning. By planning and reasoning, I mean you can just reason through chain of thought prompting or react prompting, so you don't have to learn anything. You can just prompt your model to do some reasoning. So this is the red. Green is a fine-tuned system, fine-tuned end-to-end system like we had before. It is just trained on, the gold standard data that we have, the gold data that we have. And then the purple is the system that I was talking about, where you're planning and you're learning the reasoning via reinforcement learning. And across all dimensions, the purple system that has the learned reasoning component does best. Creativity, it is much better. Language too, and overall, the differences are quite big, which is good news. It's good to see that given this improvement metric, and given we can do all of that for free without expensive judgments on story quality. Okay, so where do we go from here? First of all, evaluating this collaboration should be future work. So we actually have not evaluated how well the different LLMs collaborate. We show the collaboration helps, but maybe it's not effective the way they collaborate. Unfortunately, there is no agreed upon and detailed evaluation methodology. So there's also no agreement as to how you should design these multi-LLM systems. So should we learn their configuration for the task at hand? Should we actually, how should we do this? Is this a good idea, or just engineer them, hard code them? Ideally, you should learn it, but it's not clear how to learn it. Even with reinforcement learning, you have to have rewards. What are the rewards like and whatnot? Another important problem is that not every sort of task is appropriate for this multi-LLM approach. So we don't have a good feel for the tasks where this would be good. So there's no benchmarks. Designing tasks and data sets where multiple models divide and conquer complex problems would be very interesting. I think slowly now, like very recently, there have been some papers along these lines. And then finally, there are many levels of LLM collaboration. I only talked about inference. I only talked about what happens when we actually want to generate something. But you could imagine that collaboration takes place at the pre-training stage and at the post-training stage. And maybe this is more fruitful because then you can intervene earlier rather than once you've had a trained model. I think I'll stop here, and I'll take your questions.
Thank you, Mirella. Thank you. This was an exciting talk. I really love how you put together the last thing, like agents and reasoning.
Thank you. Too kind, too kind.
Yeah, in generation stories, I loved it. So let's see if somebody has a question. Otherwise, I do have my own.
Of course.
Well, in the meantime, so we have also been thinking here in our center how to exploit this using reasoning. So the reinforcement learning with verifiable values. So I really love that you managed to use something which is not on math reasoning. But one question which arises is that, did you try to fine tune directly on the traces instead of using reinforcement learning?
We don't have that's a good question. We don't have the traces. So the traces are part of the generation. We don't know what the traces are good or bad. We did, though, use Quen, which is a model that can actually do, so they've pre-trained it and it is able to generating a trace. So part of the learning ends up with learning a trace that is different from what it started with, because you do this iteratively and you sample and whatever. And we did not, and I guess this is it's not what you're asking me, but I will say it anyway. We actually need to look at the traces in more detail. So we don't have the traces. We could not have trained on the traces. Now we have these traces. An important question is, how do they look like, and are they meaningful? And it could be that the next generation model you seed with these traces that we have now, provided they are good. Although there's again different schools of thought. There's some people, like for the tasks I talked about, you want the traces to be meaningful. It doesn't make sense if they're not. But there are these people in mathematical reasoning where they do these experiments with random traces and meaningful traces, and they show no difference. Performance improves anyway. So,
Yeah.
Yeah.
Yeah, it's very exciting because it is the very last, so the very current results that we are seeing. So we'll have a look on the details. So we have a raised hand by Camilo. You can take the mic, Camilo.
Yeah, hello.
Hello.
Thank you for your very nice talk. I have a question. I'm not really, very familiar with the latest state of the art on reinforcement learning for LLMs. So sorry if maybe my question is going to be super naive. When you speak about the policy model that you are training, does this refer to the whole multi-agent system? So you have somehow some kind of joint laws for all these different, upstream agents, or how does it work?
Good question. Yeah, if you were, I'm wondering what question you would ask if you actually knew about this. Okay, no, it's true. This is not for all of this. So if your question is like which part of this is trained, the only part that is trained is this pink here, which is again what we put on the scratchpad. But and I did not explain this very well. The way to train this reasoning agent is it takes all the blue bits, the summary, the character, the synopsis, and whatever. This is an input, and then the policy model is trained. So all of that stuff is trained, given this as input, and then the generator is basically not trained. It's like frozen and takes all of that again as input, which we call orchestrator here, which is kind of like, to make it sound fancy. And then it generates the story output. So only the pink bits here are trained. Everything else is like the orchestrator calls this in order, provides this as input, and then we iteratively do RL in the pink part. And then once training finishes and we're happy with, how the perplexity looks and everything, then this again is part of the system, and we do it on test data.
Okay, thank you, Miguel. I wonder, it's already 1 hour. do you have time for just another question, or do you need to
Sure,
rush?
I have time. I have time.
Okay, very good.
Time.
So I do have a question of my own. Anybody else? Maybe in the chat. Okay, so I have a general question. One of the motivations of the agent work, well, not really the motivation, but one of the issues that you raised is that maybe one model might not be best for all, all languages, all domains, all tasks, all skills. This is something which we are seeing for when we try to optimize a language model for a language. So when we base our work to get the optimal language model for Basque, based on open models, we find that actually we can improve the results. So I think we have the best open model for Basque. But we always wonder what will happen if instead of having these open models, which are limited, and we can only train 70 billion, right? So what will happen if we had really all the GPUs and all these huge models that the big tech can build? So this is a general question, but do you need to fine-tune each agent on its own, or could you have lots of GPUs, train a single model with all the different tasks, and maybe use tokens to
this is a very
some other
good
prompt to guide the agent in doing one thing, just producing the plot and not writing the story. So I just wonder. I know it's a difficult question, but it's something which it's something we have in mind, and very difficult to prove whether it's so. When you work in academia, you can build the best open model for Basque for sure, but we cannot still say that if you had all the GPUs, we could have built the best model for Basque, which is also the best for the rest of the languages.
Yeah, that's a difficult problem. So I think my answer would be, even if you could do what you're saying, if you had all the GPUs and whatever, you would still need to have some way of dealing with new things that you haven't seen before. So this could be, it doesn't have to be a multi-agent system. This is if we have to be completely honest, this is kind of a roundabout way to sort of do the combination of what one knows and what one doesn't know. But you have to have adaptation. This adaptation now could be, some form of LoRa, or some form of, something. You have to have this capability, because all the GPUs in the world will never be enough for the stuff that you haven't seen. Right? Even in Basque and whatever, all these languages. So my point would be that it's not a GPU problem, it's an architectural problem, and the way we do pre-training. So we would have to change it, like, we're trying to make these agents collaborate, or they have to communicate. If you pre-train with communication and there's dialogue and whatever, then maybe you don't need to do the downstream, instruction tuning to that extent, or to the alignment, because of the pre-training being kind of broken, in my opinion. Then we have to do all this other stuff. So yeah.
Oh, sorry, I have a problem with mine. Okay, sorry, I had a problem with the mic. Yeah. Okay, thanks. So this is really something, so this one model versus, you could still have a multi-agent system where you have a single very general system which answers differently depending on what you ask. So copies of the different agents.
Yeah.
Or you could have specialized agents, which I think the multi-agent idea is great. I just wonder if it needs to be differently fine-tuned models, or just the same ones playing different roles.
Yeah, you can do that. So you specialize it differently. What would make it really multi-agent, though, it would have to be this memory. They would have to have access to each other's outputs and inputs and whatever. You can have a single model. We specialize them, but no, you could have, like, particularly if you have GPT-style models that are very good generally, and they can be specialized and they do code well and whatever, then of course what you're saying makes sense. And also the multi-agent systems, I did not say this, but inference takes longer. And this is what we see with all these reasoning models and whatever. delegate all the problems to inference. And so you think more, you take more time. Sometimes you don't want to do that, right? If you have like something and you need fast throughput, input, whatever. So maybe then you don't want the multi-agent system.
Okay, very good. So thank you very much for your time.
Pleasure.
And time for the great talk. I would like to a round of applause, even if it's
thank you.
or it's virtual. Okay, thank you, Mirella. And I want to say the last words about the seminar series. So I will post now, when we finish, the slide where you have the URL, where you can watch the recordings of the previous talks of this year and previous years. And hopefully we'll have an exciting seminar series next year as well, with this great lineup as this one. Okay, thank you all for coming.
Thank you.
Thank
See you guys.
See you. Bye-bye.
Bye-bye.